A company produces plastic bottles, and they produce millions every day, so they're not able to check every bottle for defects. Instead, they check a sample of bottles each day, and if that proportion is too high, which they classify as over 7%, they will make machine adjustments the following morning. So they take a sample of 400 plastic bottles off the production line, and they find that 16 are defective. We want a 95% confidence interval for the population proportion of defective bottles produced that day. We can start by finding our sample proportion, which we can do by dividing the number of defectives, which is 16, over the total number of bottles checked, which is 400, and we get 0.04. Our sample size here then is the 400 bottles that were checked. You can verify that if you take n times p, you'll get back the 16 bottles, that is greater than 10, and n times 1 minus p will be the non-defective bottles, which are 384 of them, and that's also greater than 10. So the conditions that we're going to need to be true for our confidence interval are valid here. Now what we want is a 95% interval, and when we use a 95% interval, our z that we use in our formula is 1.96. The reasoning behind that is if you take the standard normal and you look at the probability between the positive and negative of the number 1.96, you'll find that it's 95% in the middle. So that is where the z comes from for our 95%. So the formula says take your sample proportion, 0.04, add or subtract your z, which we said was 1.96, times your standard error, which is p of 0.04, p hat of 0.04, times 1 minus p hat of 0.04 over your sample size, which was here 400. So we get 0.04 plus or minus, the quantity will be 0.0192, so we call that our margin of error. If you take 0.04 and subtract 0.0192, you'll get 0.0208, and if you add, you'll get 0.0592. So it's likely that the total fraction of defective bottles for that day is between 2.08% and 5.92%. In this case, those are under 7%, and the machine would not need to be adjusted the next day.